Assalamualaikum everyone. We move to chapter 8. It's still about comparative static analysis, but this time it's about general function models. So what does it mean by general function model here? So let's look at the example first. So these are the examples that you already knew because you learned it from the principle of micro and macro. Okay. So let's say we have simple national income model, which is given by expression 1 and supported by expression 2. So equilibrium for national income says that whatever being received must be equal to whatever being spent. Whatever being received is income. Whatever being spent is here aggregate expenditure. Okay. All right. So y equal to c plus I plus g. As you can see, in this function, it doesn't show you any value for C or I or G. Okay, so you can't add all of C plus I plus G to get the final results of Y. And as you can see here, C here is written in a generic form. C is a function of Y, income, and also T, taxes. All right, whether Y can affect C positively or negatively, all right, or T can affect C positively or negatively, this thing you can't find in mathematics. You have to find it in the study of economic theory, all right? But we know that in the economic theory, this one has positive relationship with consumption. This one has negative relationship with consumption. Now, we can substitute 2 into 1 here so that it can yield, expression 3 here. So we have y equals to c as a function of y and t plus I plus g. Now, the next question is, which variables are endogenous, which variables are exogenous? Now, what does it mean by endogenous? What does it mean by exogenous? Endogenous means you can see that variables depends on other variables that can be written in, can be seen in the equation or mathematical expression like here. So for instance, y is endogenous because y depends on c and I and g, isn't it? At the same time, not only y is endogenous, but you can see c here. C here depends on y, okay, and depends on t. So what is exogenous here? Exogenous is when the variable does not depend on any other variables that is written in the equation. So that is a simpler way to understand it. But actually, exogenous means the variable, the determinants of that variable is not within the system or function itself. So it is very obvious that I and G are exogenous variable. Now, given this kind of function, which is a generic function or very general, how can we find equilibrium income? Here, any suggestion? All right. Now, actually, there is no clear cut to find equilibrium income here because we don't have reduced form solution that can be obtained. Why? Because obviously it's just alphabets and we don't even know the coefficient or parameters for each of the alphabets. Yeah, all right. But anyway, let us suppose that the equilibrium solution y star exists. Okay, then equation 3 can be written as equation 4 here. So we have y star equals to c star as a function of y star and also tax t plus I plus g. Now, as you can see, we only have two variables with y star. With a star, there are y star and also c star. Why? Because these two are endogenous. Therefore, these two, if you give number, can be calculated from 4. Now, there is no a star sign for t and also for I and also for g. Okay? Why? Because you know that it is all of them are exogenous, so they cannot we cannot calculate them if anything affecting them because the factors that affects them are outside the system or equation. Now, this expression 4 is actually what we call equilibrium identity. Now, and if you look at 3 and 4, we have y, and if it is in equilibrium, we have y star depends on c or c star, and in return, c star also depends on y star. Okay, now, so here c here is not an independent variable, yeah? So because c also depends on y, okay? So if this is the case, can partial differentiation be used in this case? Yes or no? To answer this, that's why we need to learn the new 3 different things here. They are total differentiation, total derivative, and differential. Okay? But anyway, this one is incorrect. Okay. Now, let's look at the first one, differentials. Okay, maybe to some of you, if you haven't studied in, in the high school, these things is very new to you. Okay, now, okay, differentials and derivatives. So we already learned that the derivative dy over dx is actually f prime x. If let's say you have y equivalent to fx, so you can see the only variable that affects y is x. So when we want to find the derivative, we can write using d instead of delta, yeah? dy over dx. Okay, and we already know that the derivative is actually the limit of difference quotient, and the limit of difference quotient is this one, isn't it? So dy over dx can be written as f prime x equals to limit of change in y over change in x as change in x approaches 0. Now, so that means dy over dx can never be the same as change in y over change in x. Why? Because dy over dx is actually the limit of change in y over change in x as change in x approaches 0, isn't it? Alright, now, therefore, we can rewrite 4 here as follows. Yeah, so you can see what we do here is that change in y over change in x minus dy over dx equal to delta. Where does delta come from? We just want to show there's a number of that shows there's a difference between these two terms. Okay, so where delta approaches 0 as change in x approaches 0. Okay, all right, now mistakes here is just change in x. Now multiplying through 5 by change in x and then rearranging, it yields the following. Okay, so I want you to do from here, okay, go to here, multiply left hand side by change in x, multiply right hand side by change in x, and then rearrange until you get delta y only on the left hand side, the rest on the right hand side. It should be easy, yeah? Okay, now, so change in y is equivalent to dy over dx times change in x plus delta change in x. Okay, now if you look at this one, we already know that dy over dx can also be written as f prime x. So we can write it this way as well. All right, now, what does it mean by equation 6? Okay, in other words, what does it describe? Actually, it describes the change in y that results from a specific change in x. All right, so you have change in y. Okay, so when you have change in x, it leads to change in y. Okay, from any starting value of x. It could be 0, x equal to 0, x equal to 1, x equal to 10. Okay, so basically from any starting value of x in the domain function of y as a function of x. Okay, now as we can see, all right, so when we look at this here and this, okay, so when delta is approximated to 0 as it, then we can rewrite this as what? So when this one is approaching 0, this one also approaching 0, isn't it? Then this implies change in y equivalent to f prime x times change in x, isn't it? Okay. Now, let's use graph to explain this. Okay, so let's say we put y on the vertical axis, okay, and then x on the horizontal axis. So let's say we have a curvy curve which is convex and upsloping. So it may look like this. And then let's say we pick one point. We call that point point A, okay, and then at point A we have x naught, okay, and then here we may have y naught, and then we draw a line that connects point A to another point to the right of the curve. Let's call it B, and then we have here, if we drag down the line, then we can have x1. Now this x1, so you can see that x0 has increased to x1, and then here is actually change in x, isn't it? So x1 is actually equivalent to what? x0 plus change in x. Can you see? Okay, so here x0 moved to x0 plus change in x. Okay, this is shown by the movement from point A to point B. Okay, on the graph of where we have y as a function of x here. Okay, so this is the generic function of it. Then how to measure the slope of AB here? So here we have y1, isn't it? Okay, so let's say I draw this line, and then let's say I put one point here. I call it point C. So here we can calculate the slope of AB here by having CB over AC, isn't it? So slope is actually the first one, is actually CB over AB, isn't it? Okay. All right. Now CB over AB is actually change in y over change in x, isn't it? So this one is change in y. Okay. Now, but let's say instead of using A and B, we draw another line that passes through A but doesn't, intersect with A, and then that line is this one. So it becomes a tangent line that at point A. Okay, so you see here, let's say point AD. Okay, this line is AD. Okay, now, so when we have another line AD here, we can also have another slope. Okay, then another slope here is basically CD over AC, isn't it? Okay, so CD over AC. So what happens here is that when line AB, move down to line AD, you can see that initially AB, the change in x is between x0 and x1, or x0 plus change in x, isn't it? But because now AB has been replaced by AD, the change in x now approaches 0 or almost 0 here, isn't it? Because when you try to calculate the change, is extremely small. Okay, so here AD replaces AB line, okay, to approximate the change in y value. Alright, so you can see change in s becomes smaller, change in y value also can be approximated. Okay, so here, from here we get extra another line DC, okay, or CD. Okay, now, so can you see, when we have AD, we have DC, but then this one, BD, is a whisk, isn't it? Or a discrepancy, or another word we can call it error. All right. So in this case, we have basically what happens here is that as change in x decreases, you see here, initially change in x is this much, but then when AB moves to AD, change in x decreases, isn't it? Become too small here, all right? So point B here slide down towards A, okay? How it slide down toward A? Because a line AB now has reduced, moved to AD, okay? So, and as we move further and further, if you have another tangent line, for instance here, then from here to here, compare with here to here, the discrepancy is this much only from, let's say, DE. And the discrepancy value becomes smaller and smaller. Hence, the discrepancy is reducing. And in this case, okay, we can see that f prime x, okay, or dy over dx is actually what? Becomes a better approximation to change in y over change in x. Okay, so this is another way to explain the concept of derivative, but then we use this kind of concept to explain the differential as well, and also total derivative afterwards. Okay, so I hope you can understand this bit, although it looks so difficult to understand, but it's very important for you to read the textbook again and again, yeah? All right, now, let's see, we move to the second graph here. I just want to talk about the line AD, okay, so that it won't be a mess like in the first graph. So we have y here, we still have the same function, y as a function of x, and we have x here. So let's redraw the curve, the curvy curve. Okay, then we have point E here, and then we have x naught here, and then we draw the line like this, and we have something like this, yeah, and then this one is D, this one is C. Okay, so let's label AC as dx, let's label CD as dy. Okay, then we can have what? We can have dy over dx, okay, which is, because it's a tangent line, therefore we can also write it this way, f prime x, isn't it? Okay, now, and if you look here, all right, it is actually the slope of the tangent AD, isn't it? Okay, and from here, so let me rewrite in here. So if we multiply this expression on both sides by dx, then what do we obtain? What we will obtain? We can obtain something like this, 7. Okay, so what you need to do here is that, so we have dy over dx equals to f prime x, isn't it? So multiply both sides by dx. On the right hand side, so you have dx. On the left hand side, you have dx. Cancel, cancel. Then you have 7 here. Okay, so basically, if you look at 7 here, on the right hand side, you have this, isn't it? F prime x. So what is f prime x actually? It can be interpreted as what? Factor of proportionality between two finite changes of dy and also dx. So it means if we have a specific value of dx, let's say 10, yeah, then we can have dx times f prime x, isn't it? So as to get the value of dy, yeah. So here, the quantities of dy and dx are differentials of y and x respectively in it, okay? And so here we can see also dy on the left hand side is actually a dependent variable. Why? Because it depends on f prime x and also dx. And just imagine, yeah, because to show that it is dependent on dx, what happens if dx equivalent to 0? Then dy obviously becomes 0, isn't it? Simple math. What if dx is not 0? Dx, let's say, positive value, let's say 10. Then dy is actually 10 times f prime x, isn't it? Okay, so here we can say that the differential of dy can only be expressed in terms of other differentials, isn't it? And in this case, dy can be expressed in terms of other differential, and that other differential refers to dx. Okay, so so when we want to calculate dy from this expression 7, how do we call this process? This is what we call differentiation. Okay, now let's try to connect this with the economic study. So let's say dy here refers to the change in consumption. Let's say dx here refers to the change in income. So f prime x is a marginal, isn't it? Marginal value. So let's say this one is MPC. So let's say change in income is 100. Let's say f prime x or MPC here is 0.7. So how much is the change in consumption here? The change in consumption is 70. So that's the use of differential. Okay, but what you can see here is that I'm not teaching you how to get 70 here, because this calculation is easy. What I did just now is that to teach you about the concept of differential from detail, from scratch, so that you can appreciate how come we can get 70 here from a scratch. Okay, what we want to do now is basically to apply differentials concept with the point elasticity in the study of microeconomics. So actually, point elasticity is one of many examples of the use of differentials. So let's say we know that when we talk about price elasticity of demand, then we must start or begin with a demand function, which is given by Q as a function of P, or quantity as a function of price. So elasticity can be defined as this, but how to come up with this? So usually in your study of principle of micro, this is what you have. Elasticity of demand, price elasticity of demand is given by change in Q over change in P, and then times P over Q, isn't it? Or if we rearrange it, then we can have change in Q over Q times P over change in P, isn't it? Or if we rearrange it further, we can have change in Q over Q divided by change in P over P. So this is what I mean here. So this one is division. Okay. Now, so if we look here, all right, let's say we replace this triangle symbol, these two triangle symbol with D. So actually, if I rewrite it here, yeah, so we can replace it, then we can have like dq over q, okay, divided by dp over p, isn't it? Okay, so this is what I mean just now, expression 7. Okay, now if you look at expression 7 here, you can see, okay, this thing in it, and then you can see these things as well. Okay, so can you determine what function is dq over dp is? Okay, this is nothing else but derivative, isn't it? Derivative. Or in other words, it's actually marginal function of demand, because we know that the original function of demand is q as a function of price, isn't it? Now, if we have dq over dp, then it is a marginal function of the primitive function, demand function. And what about q divided by p? This is nothing else but average function. Okay, so if we have the whole thing here in E, let me erase the pen here. Okay, so if we have this ratio, how do we call this ratio basically? Or this ratio, because they are just the same, it's just a mathematical arrangement. All right, so this ratio is basically the ratio of marginal function to average function of demand. Okay, and you already know that the demand is basically elastic if the absolute value of this elasticity is more than 1. Okay, very sensitive to the change in price level. Okay, now unit elastic if the absolute value is equals to 1, inelastic if it is less than 1. Okay, so what I want you to do is that find ED in absolute term if the demand function is given by 1 and 2. I won't show you how to get the answer because this one is very simple, and you know you already learn it in business maths actually. We have learned the concept of differential, where we saw for one independent variable and one dependent variable in the previous sections. Now we move to the next section, in which we try to extend the differential concept that we learned in the previous section. So how do we extend it? We may have, let's say, one dependent variable, but we have many independent variables affecting the dependent variables. Okay, so let's consider the saving function here in expression 8. Okay, in expression 8 here, we have saving function as a function of income and also interest rate. Okay, and if you look here, f is a subset of c prime. That means the function is continuous and can be differentiated or differentiable. So here, all right, usually we have something like this, s as a function of income, isn't it? Then we can have ds over dy, and then ds over dy is actually MPS. But now because we have two independent variables affecting saving, then we don't use d, we use delta. If we talk about change in income affects saving, interest rate constant, or the other way around. Okay, so we use delta. But here we want to see, instead of looking at how one independent variable affecting saving, namely income, when interest rate is constant or ceteris paribus, but here we want to see what happens to saving if both income and interest rate change simultaneously. All right, then here what we can do is that we can adopt total differentials. Okay, so if we have delta s over delta y, then this one is what we call marginal propensity to save, MPS. Okay, so for MPS here, this one, if we recall back the interpretation, for every 1 unit increase in income, then it leads to how much of increase in saving, isn't it? 1 unit. Okay, but if you want to know, if we talk about differential like in the last section, so if income increases by 10, okay, saving increases by how much? This one is actually MPS times increase in income, isn't it? All right, so but then it's not only income that can affect saving, but like I said earlier, interest rate can also affect saving. So we want to see both changes. So let's say the question is, if there is an increase in income by 10, okay, and then interest rate increases also by let's say 5%. So what happens to the saving? Because usually by theory, income increases, saving increases, isn't it? But interest rate, also the same. If interest rate increases, saving also increases. Why? Because interest rate is the income that we receive from saving. All right. So we want to see how much is the increase in saving. So because this increase in income and increase in interest rate is not by 1 unit only, if it is 1 unit, we can easily look at the MPS and also the coefficient or parameter for interest rate that affects saving. But because the increase is more than 1, 10, and 5 respectively for income and interest rate, then we need to have what we call total differential here. Okay, so here if we have delta S over delta Y, it is called MPS, marginal propensity to save. So for any change in income Y, that is dy, let's say 10, okay, dy, d refers to change, equals to 10 for instance. So saving S will change and can be approximated by delta S over delta Y times dy. So this one is actually MPS times, how much is the change in income? Let's say 10. Okay. So similarly, for any change in interest rate, that is DI, saving will change by an approximation of delta S over delta I times DI. So because these two things happen simultaneously or at the same time, so we can have the change in saving due to two of these factors is given by expression 9. Okay. Now, expression 9 here alternatively can be written as this: delta S equivalent to, ds equivalent to sy subscript y dy plus si di, isn't it? Okay. So here, if you look at this term, which is similar to this, it's just another way to write, partial differentiation. And this term, which is similar to this, these two, sy and si, are just the converters that convert the change in dy and di, respectively, into corresponding change in ds, isn't it? Okay, so when you sum both of them, okay, then you get what we call total differential. Okay, so delta s over delta y times dy, okay, and delta s over delta I times di are actually partial differentials of saving function. Okay, so here, if we combine both of them, then we can get, the change in income or the change in y, the change in saving, the change in saving due to two things. The first one due to y, so we can, observe the change in saving by looking at the y direction, and we can also see the change in saving by looking at the interest rate direction. Okay, so can we change this total differential into a differential? Obviously, yes. Okay, so if let's say we hold interest rate constant, we just say that income increases by 10 here, but interest rate constant, yeah. If interest rate constant, that means DI also, DI is 0, isn't it? DI refers to the change in interest rate. Could be 5%, by increase by 5%, decrease by 3%. That will be because interest rate is constant, then DI is 0. If DI is 0, this term doesn't exist, then we are left with this one. Then it becomes what? It becomes basically somehow total differential, isn't it? Differential only one for one independent variable and one dependent variable. Now, so if we have many variables that affect saving, let's say we are not only talking about, let me do some correction here. This one should be D, yeah. So let's say we have another one here, saving as a function of income, and then interest rate, and then tax. Okay, so we have another one here. All right. So that means we can also extend the total differential to more than two variables. You can have, let's say, up to n variables here. Okay. Now, so if we try to look at the application of n independent variables here, perhaps we can see this. So if you look here, u as a function of x1, x2 until xn, so what is u? U is basically total utility. Okay, if you have utility in your self-satisfaction, you consume many goods. Let's say good x1, good x2, good x3, so on and so forth. Okay, let me do correction here. This one should be d instead of delta. All right, now then the total differential for 11 can be written as this: du equals to delta u over delta x1 times dx1 plus delta u over delta x2 times dx2 plus until n times, yeah. Or we can replace this with u1, this one with u2. They are just the same thing anyway. All right, so what does it mean here, class? This is basically the change in utility due to many goods from good 1 until good n. Okay, the total change in utility. So if let's say the x1 here we consume increased by 10, this one consumption increased by 6, let's say this one decreases by 4, for instance, then we can calculate the total utility here. How much do we get? All right, so here, what happens, okay, to du if all dxi tend to 0? So that means no change in amount of consumption for good x1, good x2 until good n. Okay, then okay, this one becomes 0, this one becomes 0, this one becomes 0. Obviously, this one also becomes 0. That means there is no total change in total utility. Okay. Now, if you want to talk further about this total differential, we can also try to apply this total differential by looking at the point elasticity. So we can also find point elasticity from this analysis. Recall back if we use saving function as a function of income and interest rate. Okay, now if we recall back the total differential function, which is 9, okay, then we can have, I rewrite it again here, okay, ds equivalent to delta s over delta y times dy plus delta s over delta I times di. Okay, now you look at this and you take this as well. Okay, so from here we can have partial elasticity for saving function. Okay, so partial elasticity for saving function is given by this. You just need to take MPS here, and then you divide it by the ratio of s over y. Same goes to saving here. You just need to take the delta s over delta I and then divide it by the ratio of s over I. Okay, so that's one application that you can think of. There are many applications of total differential basically. Okay, now if in the case of utility function in 11, because we have about n number of items or goods, then for each item, okay, the elasticity is given by this. For each item, I here refers to person number 1 or person number 2, good number 1, good number 2, and or good number n. Yes, it's up to you which one do you want to refer to. But this is actually when we have partial difference, we take the partial differential, we can use it to calculate, partial elasticity for utility function due to one good only. Okay, now, so let's say we look at this simple exercise here, yeah. Let's look at number 1 here. Okay, number 1, u x1, x2. So utility is a function of good 1 and good 2. So if you want to find the total differential, we know that total differential is du, the general formula, yeah, u1 dx1 plus u2 dx2. Okay, so it's equivalent to what? Du, u1 is what? You differentiate ax1, it becomes a times dx1 plus u2, you differentiate bx2, it becomes b times dx2. So this is the total differentiation. You try to do question number 2 here and also question number 3, and try to look at the examples in YouTube and also on other examples on the internet. There are a lot of examples that you can think of, and in fact you have a lot of resources from the internet to study compared to the textbook. But first you need to do the exercise in the textbook so that you can grab the concept before you do more relatively more difficult exercise from the internet. Now we move to another different part of differential here. So up to this point, we already know differential. We already know total differential. Differential is when you want to see the change in, y, for instance, or dependent variable when there's a change in independent variable. Okay, so only one independent variable affects y or affects dependent variable. But for total differential, we have many independent variables become factors that can affect dependent variable. Now, there are some rules of differentials that you need to follow. If you can understand the rule of differentiation, then the rules of differentials is not something difficult to understand. So we have about 7 rules here. So let's say k be a constant, a number. Let's say k equivalent to 5, 6, 10, it wouldn't change, yeah. And u and v be the two functions of the variable x1 and x2, then the rules of differentials are as follows. So rule number 1, if you differentiate a constant, of course, obviously it becomes 0, okay. And rule number 2, if you have if you want to do differential on a constant times a variable to the power of another, another constant, then you take out the constant, you differentiate un here. When you differentiate un, so u and bring to the left near constant, and then power here becomes n minus 1 times du. Now, don't forget when you do differential, it's not the same as differentiation in the sense that this bit you must write, okay, du. Usually we write up to this point, isn't it? But because it's about total differential, you need to put du as well. Now, rule number 3 is sum difference rule. This one is also easy. So it looks like this, du plus minus dv. Product rule means multiplication. duv is actually v, and then du plus u, and then dv. Okay. Quotient rule is just the same like the way you do total differentiation for the ratio of the two functions, but don't forget this and don't forget this. Okay. So rule number 6 basically, yeah. Rule number 6, this one 7, it's typo, yeah. This is just extension of sum difference rule. This is just extension of product rule. Okay, so if we look at the exercise, we have an exercise here. Okay, so let's say we look at this exercise. Let's look at question number 1 here. Find total differentials dy of the functions. So we know that dy in general is given by f1 dx1 plus f2 dx2, isn't it? So if we want to do the first question here, the dy becomes, okay, you differentiate 5x squared 1 here, becomes 10x1. Don't forget to multiply it by dx1 plus f2, which is 3 dx2. Don't forget this and this, otherwise it's not called total differential, and this is the most common mistake done by students in exams and also assignment. So we are done with total differential and differential. Now we want to move to total derivative. Now what is total derivative here? So if you look here, how can we find the rate of change of a function that consists of, let's say, 1 dependent variables and 2 independent variables with respect to each of the independent variables when these variables are related? So in other words here, you want to see the relationship between dependent variable and some number of independent variables, but these independent variables are, related to each other. Okay, so then from here, in order to find the relationship or the rate of change or the derivation or the differentiation, then the total derivative concept is needed here. Right? So usually we have all independent variables moving at the same time whilst studying the impact of the first independent variables on dependent variable, or in simpler word here, we allow all independent variables to move at the same time, affecting dependent variable without, putting the famous assumption that is ceteris paribus in the analysis. So I give you one example here. Okay, so for instance, let's say here, okay, given the following function, okay, y as a function of x and w, and however, as you can see, x is a function of w also. So here we can show it in the form of channel map. Y is affected by x, isn't it, through f function, okay, but x is also affected by w via g function, and we can also see here y can be affected by w also. Y can be affected by w also. Okay, so this is channel map. Now here w is the main or ultimate source of change, such that it can affect y directly and indirectly. How? It can affect y directly because if you look at the generic function here, W directly affect Y because it is explicitly written in the function. Okay, so W explicitly directly affects Y through F function. On the other hand, W can also affect Y indirectly via G function because W first affect X and then X affect Y. So it can also indirectly affect Y. Now, here, in this case, because these two things happen simultaneously, then how can we know what happens to Y if W and X change simultaneously? All right, so we need to add up the two effects, direct and indirect effects. Yeah, then direct and indirect effects here leads us to a total derivative of Y with respect to W as follows. So this is how we do total derivative. Okay, so dy over dw equals to fx dx over dw plus fw, or fx here is actually this, fw here is actually this. Now, if you are very good in mathematics, you can easily find total derivative from generic function straight, and you go straight to this answer. Okay, I prefer this way if I do it for my own exercise. But because perhaps some of you are still new in this, in this thing, there's another simpler way to do it. It's not simpler way, it's just that you have two steps to follow. But then these two steps can avoid you from making silly mistakes. Okay, what's these two steps? Okay, let me show it here. All right, now let me rewrite again the function y as a function of x and w. What you need to do in the first step is to find total differentiation that you have learned in the previous section. So totally differentiate expression 1, so you get dy. Okay, dy equivalent to fx dx plus fw dw, isn't it? Okay, after that, divide number 1 here by dw, both sides. So dy over dw equals to fx dx over dw plus fw times dw over dw. Cancel. Okay, then you can see that your answer here is actually similar to the last line here. Okay, so that's how you do it. Do it step by step. You don't have to be in rush. After a certain time, if you're confident, then you can do directly like what I did when I was a student. Okay, so now here, the process that we have done just now, process 1 until 2, or the faster method like I did when I was a student. Okay, this process of finding total derivative is actually called total differentiation of y with respect to w. Okay, so you have to be careful with this symbol, because some bit you can use delta, some bits you have to use d. Okay, now so from this here, let me erase it so that it becomes clearer. So let me erase this bit first. Okay, so this is number 1, this is number 2. Now if you look at this, okay, you need to recognize which one is partial derivative and which one is meant for total derivative. Yeah, okay, now let's say let's look at the exercise here. Find the total derivative for the following function. Okay, you look at the exercise number 1 here, the total derivative for the following function. So what we need to do here is that if you follow the two steps that I've just taught you just now, okay, you be careful first, you read the equation carefully. Y equal to function of x and w specifically is given 3x minus w square, where x is what? Where x is actually a function of w, and specifically, numerically, it is 2 times w square plus w plus 4. Okay, now when you are requested to find total derivative, you don't substitute x equivalent to 2w square plus w plus 4 into y function and then do partial derivative. That one is not total derivative. That one is doing partial derivative. In order to do total derivative, you must do it step by step. Okay, don't do partial derivative. So here, step number 1, take the total differential. Okay, so you have dy equivalent to what? 3x here, you differentiate, it becomes 3. Don't forget dx. Okay, minus, okay, w square here, when you differentiate it, becomes 2w. Don't forget dw. Okay, now, also, you have x equivalent to 2w squared plus w plus 4. Okay, and you know that in the second step, what you need to do is that to divide this by w, because the ultimate source of this equation is actually w. So you have dy over dw, 3 times dx over dw minus 2w dw over dw. This one becomes 1, isn't it? Okay, now, so here, dx over dw, what you need to do is that you need to differentiate dx over dw from x as a function of w here. So it becomes 4w plus 1. Okay, once you have this, substitute it here. Okay, so it becomes what? 3 times 4w plus 1 minus 2w dy over dw on the left hand side. And then you simplify, until you get, let me continue here, dy over dw equals to 10w plus 3. Then this is how you do it. Don't do partial derivative. Do total derivative. It is if the question asks you to do total derivative. Okay, now, in so what if, if we have more complicated function like in 18 here, where y is a function of x1 and also x2 and also w, but we know that x1 is a function of w, x2 is also, sorry, x2 is also a function of w. Then first, if you don't get the clear relationship between this, I strongly advise you to draw the channel map. Okay, so basically, okay, let me erase the mess here. Okay, so basically what we have here is that we have y being affected by x1. Okay, we have y also being affected by x2, and then x1, x2 affects y via function f. Okay, we also have x1 being affected by w. We also have x2 being affected by w. x1 being affected by w via function g. x2 being affected by w via function h. Now, w, as you can see here, can directly affect y. So, affect y via function f. So here there are two different direction. One is indirect, another one is direct. Direct is when w directly affect y. Indirect is when w indirectly affect y via x1 and also x2. Then you can start to find total derivative for this case. Okay, so for instance, let the production function be output q as a function of capital, labor, and also t here. T here refers to time. So capital and labor can change over time. Also, that means capital as a function of time. Labor also a function of time. So what is the rate of change in output here? So the rate of change in output here depends on three things: capital, labor, and time. Now, capital also depends on time, labor also depends on time. Now, what you need to do here is that first, draw the channel map so that you can see clearly which one is directly affecting Q, which one is indirectly affecting Q, okay? Then you can start finding total derivative, okay? Now, we also have example of, this function where we have y as a function of x1, x2, u, and v, where x1 is a function of u and v, and x2 is also a function of u and v. Okay, so can you also find its total derivative? You need to try it at home. Now, so whenever you see this kind of function, y is a function of x1, x1 is a function of u and v. Y is also a function of x2, x2 is also a function of u and v, and so on and so forth. So y depends on x1, x1 depends on u and v. Okay, so this is what we call as composite function. Okay, it is composite function because a variable is a factor of another variable and also a factor of another variable. All right, so there are some remarks that we need to know when it comes to total derivative here. Okay, so due to functionality dependent of a variable to a second one and in turn dependent on a third one, chain exists in this relationship. So I did show you the chain map. So we are talking about the chain map here. The appearance of a product or products of two derivative expressions as the components of a total derivative is the evidence of this existence. Okay, and the chain of derivative in a composite function can have more than two links. Okay, two derivatives being multiplied. Okay, you have seen this also before. And total derivatives, including partial total derivatives, measure the rate of change with respect to some ultimate variables in the chain. And this ultimate variable is exogenous, and therefore it's not expressed in terms of some other variables in the function system. Okay, so as you can see in the previous example, for instance, number 1, y is a function of x, where x is a function of w. Okay, so which one is the ultimate variable, the main variable? The main variable is w. Okay, all right, now we are done with total derivative. Now we move to derivatives of implicit functions. Now, how to do derivative of implicit function? The first thing that we need to know is what does it mean by implicit function? Okay, so let's say we are given expression 1 here. Okay, y as a function of x, in particular 3 times x to the power of 4. So if we look at expression 1 here, we can see that explicitly y depends on x. Okay, so that's why it is called explicit function. However, we can rewrite 1 as number 2. So if you look at number 2 here, y minus 3x to the power of 4 equal to 0. And therefore, if we try to write it in generic form, f, x, and y. So as you can see here, all right, initially we know that y depends on x. But in expression 2, implicitly, we know that y depends on x. Okay, we know that y depends on x because we put, all the variables on the left-hand side, and on the right-hand side is just a constant, which is 0. Now, equation 1 is implicitly defined by equation 2. So equation 2 is an implicit function. Okay, so in equation 1 here, we only have one argument, but in equation 2, we have two arguments. Now, what is argument in equation 1? Obviously, it is x. Okay. What are the arguments in equation 2? The arguments in equation 2 are y and also x, isn't it? But in this case, we only have two arguments in implicit function. Can we have more than two arguments? Obviously, yes. Okay, so if we have more than two arguments, then we can write it this way in generic form. Okay, all right. Now, on the other hand, we can also write it this way. Okay, implicit function, write it this way. Okay. Still talking about the concept of implicit function. We haven't done anything about derivative of implicit function. Now, we move forward here. Now, what are the general conditions to ensure that a given equation of implicit function like this is really an implicit function of explicit function, okay, around some specific coordinate or point in the domain? Okay, so this statement is trying to say that what are the conditions that we can have so that we know that that explicit function actually has implicit function. Because why? Because some explicit function they don't have implicit functions. So in this case, we need to understand the implicit function theorem. Now, the implicit function theorem, okay, let's say we have implicit function here written as this, okay. So number one, if this function, implicit function, all right, we have this, it must be continuous and has continuous partial derivative, okay. It must be continuous means when we draw, okay, the curve continue, for instance, like this, and no gap in between. We don't have step function. We don't have, we don't have no value in the middles and whatnot. And then that means it can also be, we can find partial derivatives such as fy, f1, f2 until the last one, which is fm here. Okay, so because the last one here is fm. Okay, now implicit function theorem, the second point is, let's say we have implicit function, okay, let's say we pick one point, okay, which is, this coordinate, y0, y10, y20, until yxm0, okay, this point, okay, that satisfy this equation. When I say satisfying this equation means if you put all of this point into the formula of this equation, it gives you answer 0. That's what it means, yeah? Then this point exists, isn't it? Then when you take the partial derivative of this implicit function with respect to y, it's not 0 also, okay? Then there exists an m-dimensional neighborhood of x10, x20 until xm0, okay? So you have m-dimensional neighborhood. Why? Because you have m number of, independent variables here, okay, and m-dimensional of neighborhood, and that neighborhood is called capital N, okay, in which y is implicitly defined function of the variable of x1, x2 until xm, okay, in the form of what? In the form of explicit function like this. Sorry, in the form of implicit function like this, because recall back in the previous slide, this is implicit function. We can also write it in this form, okay. So that's why you can see y as a function of y, x1, x2 until xm here, this one, okay. Now this implicit function satisfy the equation of implicit function should be equal to 0 for every m tuple, okay, in the neighborhood of n, capital N. Therefore, this implies that this implicit function has a status of identity in that neighborhood, okay? And also the implicit function f is continuous and has continuous partial derivative f1, f2 until fm, okay? So when it says has a status of identity, what does it mean here? Try to figure out what does it mean, okay? So this implicit function theorem sounds complicated, isn't it? All right, but actually it just want to show you that an implicit function can exist for any kind of explicit function if the implicit function itself is continuous, and when you do partial derivative for each and every single variable argument in the implicit function, it has its partial derivatives. And also when you pick one point on the implicit function here, it satisfies the the certain condition for the neighborhood of n. Okay, it means it exists there. Okay, so it sounds complicated, isn't it? So now, let's say we have this function here, f x y equivalent to x squared plus y squared equal to 0. Okay, you look at this and you look at this. Okay, so can we apply implicit function theorem for this? Can we apply implicit function theorem for this? Now, before we go into detail into that, let's look at this. Here, okay, when we look at implicit function theorem in 1 and 2 here, we says that partial derivative of implicit function with respect to y shouldn't be 0. All right. However, all right, all of these two conditions cited in the theorem is just a sufficient condition, but not a necessary condition. Okay. So if it is sufficient condition, it is a very strong condition, isn't it? But if it is just a necessary condition, it means that's the minimum condition that you should meet. Whenever I say sufficient condition, it is more than the minimum conditions. Okay, so the condition cited in the theorem is sufficient, but not a necessary conditions. So that means if we find that the partial derivative of implicit function with respect to y equals to 0 at a point, coordinate this, okay, in equation 9. So it means what? It means we cannot use theorem to deny, all right, the existence of an implicit function around that point. So what does it mean here, class? Although the theorem looks so strict, but if let's say this one, okay, is this. In the theorem, it says fy shouldn't be equal to 0. But if the case is like this, what happens? Can we say the implicit function doesn't exist? It's not really, actually. Okay, it's not really. Sometimes it also exists. Now, number 2, even if the specific implicit function exists, another problem is that the theorem does not give any clue or hint as to the specific form of the function f takes. So it means when you have y as a function of x, isn't it? So let's say 3x to the power of 4. And then you write, fxy equivalent to 3x4. Sorry. So here we should write y minus 3x4 equal to 0. This one is very clear in terms of the shape of the function, implicit function. But sometimes, all right, if you're given just a generic function fyx, okay, very generic, okay, equal to 0, and then it gives you certain condition fy is like this, fx is like, this or whatever. Sometimes you don't really know whether, the function is, concave or convex or whatever, okay, unless if you put certain additional conditions. Okay, so that's why it says even if explicit function exists, we don't know the shape of that implicit function. That's what it means by this statement. Okay, also it does not tell us the exact size of the neighborhood in N in which the implicit function is defined. So that means sometimes, most of the time, we know that theorem here, the conditions in the theorem, where we have two conditions here, are not always we can omit it. Okay, so here, although the limitations of the implicit function theorems are stated in 1 and 2, all right, this and this, okay, this theorem is still important or significant. So it can implicitly solve y in terms of x when explicit method cannot help us to find the solution. Okay, now, in this case, all right, so what does it mean here? And you might be wondering, all of this from this slide until this, I keep talking about the concept and the theorems of implicit function. But what does the implicit function mean anyway? Why do we need an implicit function when we already have explicit function? Isn't it bothering us when we know that we can solve from explicit function and still we need to have implicit function? Okay, you have to understand that for this case, y as a function of x, let's say 3x to the power of 4, this is very easy in terms of what is value of x, what is value of y, isn't it? So you can explicitly find it from explicit function. But sometimes, okay, especially when explicit function given to you is not really clear, and especially if it is given in the form of generic function. Yeah, this one is not generic function, this one is a very specific function because the number is 3 and then the power is 4. Or if it is given like this, capital X, small letter x to the power of n, then you need to know the condition of this, you need to know the condition of this. And also the question A asks you what is x, for instance. So sometimes you cannot find it directly from explicit function. The second way is to create implicit function. If exists, then you do some calculus, then you can find x is what, y is what. Or sometimes the use of implicit function is like, when you cannot get, the relationship between y and x, whether it is increasing or decreasing explicitly from explicit function, then you may need to create implicit function. After you create implicit function, then only you can find, partial derivative of y with respect to x, for instance. Okay, So this is the second use of implicit function. Okay, now we move further to the derivatives of implicit function. Okay, let's say we want to solve y using implicit function like this. Yeah, let's assume that it is possible to get solution. Okay, for y using this function. So we can explicitly write out function y. Another way to write is like this, isn't it? Okay, and find its derivative. Okay, so let's say, okay, we have initially we have this y as a sorry, we have this okay 0 equals to y squared plus x squared minus 9. Okay, if we have this, what can you say about this? If you are very good in mathematics, this one is actually an equation for, you know, a circle, and the radius of the circle is 3. How do we know? Because if you try to, you know, to factorize it, then you can see this factorization, it becomes plus minus 3. So the radius is 3. Okay, so now, if you look at 6 and 7 here, all right, so you try at home to find the derivative for 6 and 7. Also, if we draw it, we draw small like this. So we have 3 here, we have minus 3 here, we have 3 here, we have minus 3 here. Then you draw it, you get actually a circle, isn't it? Now, if we have a circle like this, then for every x, there are 2 y values, isn't it? If there are 2 y values, then it's very hard actually, if you know into detail about mathematics, yeah? It's very hard actually to find implicit function. So that's why sometimes, okay, when they factorize, you're gonna have, you know, positive part, and you also have the second part, which is negative part. So this is the positive part of y, the negative part of y. So that for every x, you have one value of y. For every x in the 7 here, you also have one value of y. Okay, now, so here, if you have it like this, what happens is that, okay, it's much easier to solve for the value of y. Okay, so here, when we have implicit function like this, if you don't put certain restriction, then you come up with the whole circle like this, then it's not easy to find y, because for every x you have 2 y's. But if you allow, you know, if you, let's say you restrict it, we only talk about y on the positive side, then we talk about the upper side here, quadrant number 1 and quadrant number 2. Okay, or if we only want to talk about the lower half of the circle, quadrant number 3 and quadrant number 4 here, then we talk about expression 7 here. Then it's much easier, you know, to solve it, okay, using implicit function to find y on the lower part of the circle itself. But anyway, this one, my explanation is not very detailed. I want you to figure it out more from YouTube and in the internet, because this kind of example is the most frequent used and very famous example to explain, you know, the concept of implicit function. Okay, now, what happens if we have implicit function like that, but then initially, okay, we want to find y. What is y? Okay, so if we have implicit function like this, we of course must have explicit function. So explicit function is y as a function of x1, x2 until xn, yeah? But when we write it in the form of implicit function is a function of y, x1, x2 until xm equal to 0. And what if we want to find y using explicit function, but we cannot do it? Then this is the use of implicit function, yeah, to find y. Under implicit function theorem, if an implicit function exists, we can still calculate the derivative without having to solve y first. How to do this? Okay, so basically, we know that, okay, y as a function of x1, x2 until xn, okay, but we know that from this explicit function, Okay, we cannot solve for y explicitly. For instances, we cannot solve for y explicitly because you have two values of y for each of x. Okay, but then our interest is not to find what is the value of y when x is like this, like this, like this. Our interest is to see the relationship between y and x. Okay, if let's say x1 increases, what happens to y? Will y increase, will y decrease, or will y maintain the same like this? Okay, because we don't know the value of y from explicit function, that's why in order to see this kind of relationship, what we can do is that transform it into implicit function. After we transform it into the implicit function, we find the derivative of implicit function. How to find the derivative of implicit function? That's why we need to know how to find it using the formula of derivatives of implicit function. Then after that, when we get the result, then we can get the results of this. Okay, so in order to do the derivative of implicit function, we need the implicit function rule. So this rule can give us derivatives of every implicit function defined by given equation. Okay, now before we go into detail about that, we need to know about three things that need to be considered in the implicit function rule. So what are those three things? Number one, if the two expressions are the same, the respective total differential must be equal. Okay, that makes sense, isn't it? Now, number two, differentiation of an expression that involves y, x1, x2 until xm. Okay, or in other words, differentiation of an expression from implicit function will yield an expression involving the differential of dy, dx1 until dxm. Okay, now number three, the differential of y, which is dy. Okay, the differential of y is dy, can be substituted out. Okay, so the fact that we cannot solve for y does not matter. Okay, so like I said, you want to see the relationship between y and x1. You don't need to find y equivalent to what. Okay, sometimes we cannot get it, but our interest is this relationship between y and x. So you perform you convert the explicit function into the implicit function, and then you find the derivative. Okay, so if we apply the above 3 points to the equation of implicit function, then we can write, okay, df equal to do, or another way is, okay, you find first this, so on so forth until this, equate it to do. When you find the differential of 0, it is 0, isn't it? Because it's a constant. Remember the rule of constant for differential. Okay, so we know that an implicit function for this has the following total differential. Okay, when you do total differentiation, dy f1 dx1, f2 dx2 until fn dxn, isn't it? Okay, and we substitute dy in 8 with 9. Okay, so dy here, we have dy here. Okay, use this, put it here in 8. Okay, and then when you substitute it 9 into 8, rearrange it. Okay, then we get something like this. Okay, can you try it at home? Because this is just a matter of substituting certain equation back into another equation and then rearrange. Then you should get something like 10 here. Okay, now let me erase it because otherwise it becomes a mess. Okay, now all the dxi, when I say all the dxi refers to what? dx1, dx2, dx3 until dxm. So I refers to number 1, 2, 3 until m. So all the dxi can vary independently from one another. Okay, so if x1 changes, it doesn't mean that x2 need to change also. Okay, because let's say x1 here is the number of apple consumed. The x2 here is the number of orange consumed. So when we have dx1 is the change in the number of apple consumed, dx2 is the change in the number of orange consumed, and so on and so forth. The total change here must lead to 0 because they offset each other. Yeah, so all the dx1 can vary independently from one another. So for equation 10 to hold, each parenthesized expression So because we dx1, dx2, dx3 can vary, okay, let's say dx1 is 3, change is 3, this one is 4, this one is 5 and whatnot, but the whole summation here must be equal to 0. If the whole summation here must be equal to 0, that means what? These things, this thing, and this thing here, okay, must equal to 0 for all I, isn't it? Otherwise, you cannot maintain this 0 value. Okay, so for equation 10 to hold, each parenthesized expression must individually vanish. This means we must have 11. Okay, this means we must have 11. Now, what we need to do with 11 is that we divide through 11 by fy. Okay, because we want to do total differentiation. Okay, we divide 11 by fy and solving for fi. Okay, then it yields the following. Now, for this kind of calculus, I wouldn't write it for you. You have to find it yourself because this one is very easy actually. Now, if you're stuck, you cannot find it. A lot of video on the YouTube can show you how to do it. And this one is very easy to do actually. Okay, so now you can get fi. Okay, I refer to 1, 2, 3. So let's say if we have x1, so if I write f1 means the partial derivative of y with respect to x1, okay, is actually equivalent to fi over fy. Now in this case, f1 is actually partial derivative of y with respect to x1 is actually equal to minus f1 over fy. Okay, then this is the use of implicit function actually, because you can see the relationship between one argument with y, okay, although you don't know how to find y, okay, because for instance, if I use economic example here, we know that GDP and consumption keeps changing, and let's say consumption is a component of GDP, so means if consumption changes, GDP can also change, isn't it? So, but most of the time, we don't know what's the value of, GDP, because we can only know the value of GDP towards the end of the month or quarter or the year. But we are more interested in the relationship between GDP and consumption. But because we don't know how much is the GDP increase from one time to another time, then we have the equation of GDP and consumption. Then the best way to find this relationship is to turn this equation, GDP as a function of consumption, as GDP and consumption as two arguments which is equal to 0. Then you can find the relationship using formula in 12 here, okay, and then you can get the sign whether it's positive or negative. So equation 12 is the implicit function rule for finding partial derivative fi of the implicit function this. Okay, in the simple case where given equation is fyx, the rules gives this one 13. Okay, so even if the specific form of the implicit function is unknown to us, okay, we don't mind about that, but what we really mind is we want to find its derivative having the negative of the ratio of a pair of partial derivatives of function f here that defines implicit function. Why we want to know its derivative? Because we just want to know about the relationship between y and the argument or the other independent variables. But in this case is for the case of fy not equal to 0. Okay, sorry, but this case is for the case of fy not equal to 0. Yeah. Okay, let's look at some example here. Let's look at the first example. Find delta y over delta x. So this is an implicit function here. So delta y over delta x is actually what? Minus fx over fy, isn't it? So here, fx is what? So 2x y cubed, isn't it? Plus yw. And on the denominator, okay, 3 x squared y squared plus xw, isn't it? and don't forget the minus sign. Okay, so that's the first example. Now let's look at the second example, which is more related, which is economic example. So usually we have quantity as a function of K and L. This is the explicit function, but we change it to implicit function. So implicitly defines a production function of this, isn't it? So we need to find MPK, marginal product of capital, MPL, marginal product of labor, and then delta K over delta L. And here, how to find MPK? All right. So to find MPK here, it's very easy. Delta Q over delta K, isn't it? If there's a change in capital, how many quantity changes? So that is marginal productivity of capital. Okay, so it's this FK minus FQ, isn't it? That's the answer. Yeah, we cannot simplify it further. Why? Because we are given generic form only. Okay, what about, so this is MP. Okay, so I hope how to you know how to find MPL, yeah? So I won't show you. Now what about dk over dl? Okay, so dk over dl is actually what here? And if you study in economics, dk over dl is what? So I want you to figure it out, try to find the answer, because this production function is among the most frequent used function to study implicit, function theorem, and also derivative for implicit function. So good luck. And okay, now we move to the last subsection of this chapter, which is comparative static of general function model. Now, so from here we can see the use of total derivatives. Okay, so let's say we consider a single commodity market that has the following. Okay, so in a market, of course, you have quantity demanded equals to quantity supply when we have equilibrium, and quantity demanded is expressed by this equation. Quantity demanded depends on price and also income. Why not? Such that, okay, in terms of price, it is negatively related here. In terms of income, it is positively related. And we have the second one here, quantity supply. Okay, quantity supply, depends on price, such that the relationship between quantity supply and price must be positive. And all of these are basically law of demand. This one law of demand. Okay, this one is law of supply, and then this one is the determinant of demand. Okay, now we know that in the equilibrium condition, equilibrium condition is this. So this is basically a explicit function, and then QD is given by this, QS is given by this. So we actually can rewrite it in the implicit form. So here QD minus QS equal to 0. Then when we have this, specify it further, then we can have this, isn't it? Okay, once we have this, well, here we want to find price here, we also want to find price here. Then okay, so here where price is a function of income, isn't it? Okay, and so could you take the total derivative of the equilibrium identity above with respect to income? Okay, then once you have it, then you solve this one. So how to do it here? Before we take the total derivative of 15, let's recall back this one. If you see this, okay, that means demand minus supply equal to 0. That means what happens to excess demand? Excess demand is equal to 0. What happens to excess supply? Excess supply also equal to 0, because when we have this, it means equilibrium condition has been met, isn't it? And here, like I said earlier, price depends on income here. So we have expression 15 here with the condition of this. Could you take total derivative of 15, okay, on equilibrium identity above with respect to y? So how do you do it? Like I said in the previous slides, the total derivative here, you must follow step by step. Step number 1, okay, you take the total differential. So when you take the total differential here, okay, so you have what? You differentiate demand with respect to, let's say, income, for instance. Okay, So or price, for instance. So first, differentiate demand with respect to price, and then change in prices like this, isn't it? And then at the same time, because in demand we also have income, okay, differentiate demand with respect to income, partially differentiate, multiply by change in income, dy. So we are done with demand. Okay, now next, okay, we do supply, but before supply we have minus sign here. We differentiate supply with respect to price, and then change in price, isn't it? And then equal to 0. Second step, divide both sides by dy. When you divide both sides by dy, you reach 16. You try it at home. Okay, now when you reach 16 here, 16 here can be divided into 3 different parts. This is the first part, the second part, and the third part. If you look at the first part here, it's actually indirect effect of Y on demand. Why? Because Y first affect price, then price later affect demand. Okay, so that's why Y can indirectly affect demand through through price. Okay, now next, in the demand we have income. So income not only indirectly affect demand, but can also directly affect demand. So that's why delta D over delta Y naught is direct effect of Y naught on D. Okay, so in the demand, on the demand side here, we have direct effect of income and also indirect effect of income on demand. Now, we move to the supply side here after minus sign. Okay, so because we are totally differentiate the function with respect to Y, yeah. So as you can see, okay, quantity supply depends on the price of supply, but we know that the price in the market depends on income. So as you can see here, when we want to see what happens to supply when income changes, it's basically given by this bit, and the third here, the third terms here before equal sign, and the third term here shows that how income affects supply. Income affects supply indirectly. Okay, income first affects price, and then price affects supply. All right, so by doing this, we are actually doing comparative statistics of general function models. Okay, now also in the simultaneous equilibrium approach, there is a pair of equilibrium identity that we can see. So here, quantity demanded minus equilibrium quantity equal to 0. Quantity supply minus equilibrium quantity equals to 0, where price depends on income and quantity depends on income. Okay, so can you draw a channel map to show various effect of Y on, price and also quantity demanded and also quantity supply? You should try this at home, because the channel map I have shown you earlier when we did, differentiation previously. So basically, Y naught can directly affect D function, but it can also indirectly affect D function through P, isn't it, price? So these two effects can be detected when we differentiating D function with respect to Y naught. So if you want to know whether certain variable affects dependent variable directly or indirectly, then you can do this kind of differentiation, total differentiation or total derivative method here. Okay, now there is only one indirect effect of Y on S or supply. This can be determined when we differentiating the S function with respect to Y, isn't it? I have shown you earlier. So what is the results of total differentiating the two identities with respect to Y naught? We will have the following, isn't it? Okay, so if you bring, delta Y over delta Y naught minus sign here to the right, okay, then you can rearrange it and you can get something like this here. Okay, here there's some correction here. This one should be delta S over delta P not D, and then the first one here, you know how to do it from the previous equation, which is this. Okay, you bring this one, Okay, you bring this to the right here. Okay, and then if you see this, okay, this is basically come from total differentiation of supply function in equilibrium position. The first one here and the second one. The first one here is total differentiation of demand minus equilibrium quantity. The second one here is total differentiation of quantity supply minus equilibrium quantity. Okay, now so this is just one example in economics. Yeah, there are some other economic example for implicit function rule for general functional form. So if you look at the textbook, it will talk about the ISLM model. And if you look at the Sham's outline, okay, introduction to mathematical economics, then you can see a lot more of example that use implicit function rule. Okay, so I hope you go and find them and try to do all of this kind of exercise on your own. Okay, so that's it for this chapter.